G'day viewers. In this segment we're going to talk about internetworking, or how to combine multiple networks together into one larger network. So internetworking, or connecting all of these different networks into a single larger network, is difficult because the networks we might want to connect might be very different in terms of how they operate internally. They can just be different in many ways. I'll go into some in a moment. And what we would really like to do with internetworking is to paper over these differences so that we're able to connect from hosts on one network to hosts on another network as though it was a single network. That sounds kind of hard. It is hard. It doesn't always work. What we'll do to learn about internetworking is we're going to essentially look at IP. IP is a case example, if you like, a case study, but it's the most extensive case study around, and it has a lot of experience with how to combine different networks together, because IP, of course, is the protocol that grew up into the internet that connects all of the different kinds of networks today. So how might networks differ? If we're going to interconnect them, we need to understand some of their differences. Basically, they can differ in a lot of ways, and we're not going to be able to resolve all of those ways. I talked about, in an earlier segment, for instance, different kinds of network service models. Suppose you have a network service model using datagrams in one network and one using virtual circuits in another network. Imagine combining these. It's a little like combining the post office and the telephone network. It's not clear that would work very well. Different networks might have different kinds of addressing, since they'll normally be designed by different people. So they might have different kinds of addresses. So it's not clear that we can even write the different kinds of addresses in the right place in other networks. And there may be many different features in these different networks. They can range from large to small. A fairly large one, for instance, might be quality of service. Imagine if one of the networks has multiple different kinds of qualities of service. Maybe it has regular packets and packets that are priority packets, which should be afforded ahead of regular packets. And another network doesn't, it just has basic service. How are we going to combine these networks and still honor the quality of service arrangements of the one network that uses quality of service? It's not clear. Smaller examples of a difference might be that different networks can typically handle packets of different sizes. Is this going to be the case? Yes, it's the case all of the time for technological reasons. Different kinds of link layer technologies can handle packets of different maximum sizes. This seems like a small mundane detail, but even this detail actually turns out to require a lot of work from the architecture to deal with, let alone larger things like networks that have different kinds of quality of service or security. The job of internetworking is to hide all of these differences across networks with a common protocol. If you think that sounds kind of tricky, you're right, it is. Just to give you an example and sort of get into the flavor of how we might connect these things, I'll talk about connecting datagram and virtual circuit networks as an example. So suppose that you have a source sending to a destination. The source is on a datagram network. The destination is also on a datagram network. And here in the middle, I put a virtual circuit network. Oops. Just to make things a little tricky and bring up some of these issues. So let's imagine what's going to happen when you want to send from this source to this destination. We have the packet here on the left. So first of all, you'd need to be able to write the destination address in this packet, even though the formats might be different because one's on 802.11 and the other's on Ethernet. Suppose we could do that and we send this packet into the network. In the datagram network, it will be forwarded using the destination address all the way through a router at a time until it reaches the virtual circuit network. At that point, something needs to happen. This individual datagram needs to be mapped to the right circuit, and it then needs some other identifying information that it didn't have, the circuit identifier, slapped on it, so that it can then go down this circuit, and that circuit will take it all the way maybe across the network, if in our case it's going across. At the other side, we're back on a datagram network, so we can forget about whatever virtual circuit it came from. I've described the transition here as a bit of a bump in the road because suddenly you have to do a lot of potentially unusual things. For instance, this circuit needs to be set up. If it wasn't set up ahead of time, then we would need to hold the packet and wait while setting up a circuit. That's a bit of a daunting proposition because packets can arrive fairly fast, and so in MPLS, for example, the circuits are already set up ahead of time. Even so, we'll have to have some sort of special table to look up how destination addresses, well actually it's more than destination addresses, it's how packets from a certain source to a certain destination should be mapped to circuits, virtual circuits that go across the ISP network. So we'll have to do that at the ingress, and at the egress we'll have to take off the virtual circuit information and so forth so that it can go into the datagram network. So you can see that this adds some amount of complexity. Well, internetworking is a topic that's been around for a fair time. In fact, it was pioneered by Vint Cerf and Bob Kahn. You can see their pictures here. These two are widely credited as being the fathers of the internet. They began working on internetworking in 1974. Internetworking is what really led to both TCP and IP. The early internetworking protocols kind of combined some of these functions, and it was only later that it was divided into TCP, transport layer functionality, and IP, the network layer functionality for datarams that we're looking at now. Their work tackled all of the problems of interconnecting these networks, and really in some ways their key insight was that of internetworking, that they would find some way to connect all of these networks instead of, for example, mandating that a single link layer technology, a lower layer network technology, be used. If you only had that single lower layer network technology, it would be fairly easy to grow larger networks because we wouldn't have to deal with all of these differences, like some networks use virtual circuits but others use datagrams. However, if you've been around the block more than once, you'll realize that mandating a single network technology is something that would never have worked. There are many different reasons, technical and non-technical, for using different networking technologies. And so it's very much to our advantage if we can have some way to combine them. That's what we do with internetworking and IP. This slide here is actually one from one of our early lectures. And I put it up just to remind you of what sort of happened with IP. IP has been this layer to which we want to put all different networks together, and so the different link layers and transport layers all essentially conform to IP. And IP, because connecting these networks is so valuable, has become the narrow waist of the internet, as it's called. It's shown to be narrow here because there's somewhat of an explosion of link layer technologies and different applications. Both the link layers go below and the transports and applications go above. And IP is the glue that's really holding all of this together. So these days, if you come up with any application or networking technology, there's great pressure for it to conform to IP. There was less pressure, I guess, in the early days as IP essentially emerged, as all of the different networks sort of worked out what they would have to do to be able to connect together. A result of a lot of that pressure is that IP really is forced to become something of a lowest common denominator service. If you think about it, just imagine for a moment this hypothetical case. Suppose that you have two networks and one of them has good support for quality of service, priorities or different priority levels, and the other has nothing. What's going to happen if you internetwork them and combine them together? You can combine them, sure. Let's say you could send a packet, a normal priority packet, from one network through to the other network, and it will just go through. But it's going to be difficult for you to preserve this quality of service feature, since inside the network that doesn't support quality of service, you have no easy way to distinguish between the high quality and the low quality of service packets. As a result, IP tends to be pushed to be the kind of lowest common denominator. It asks very little of the lower layer services, essentially the ability to deliver packets to where they're sent. That's it. And as a result, because it asks very little of the lower link layers, it's only able to provide it gives very little extra to the higher layer services. Essentially, it's a glorified way to deliver packets through the network. If applications want more than that, well, they're going to have to build transport layers and application processing of their own to provide higher level services which do more for us. But this approach, nonetheless, of having the lowest common denominator service proves to be very useful because it does allow this glue to essentially combine everything together into one internet. Well, here is the picture of the IPv4 header and a payload following it. Often the best way to find out what's going on with a protocol is to look at the format of its messages, because they tell you the information that's been exchanged. This picture here shows us what is going on inside the IP, inside all IP packets, and it really focuses on the IP header because that's where the action is. This last bit here, payload, this is just the data that the packet is carrying. So if the higher layer is TCP, this would be a TCP segment. Now these diagrams, you might not have really seen them much before. This diagram shows us the order in which information is put in a packet. You might imagine that it's difficult for us to draw a packet as a very, very long yet thin line that goes from left to right. Our page isn't wide enough. So instead, it's common to see diagrams drawn in this format. You read it from left to right across one layer and then the next layer going down. So left to right, top to bottom is the way we read all of these bytes. This really corresponds to the one long line. So you can see here what this means is we begin at the top left with it says the version field. And this diagram is 32 bits wide. So every time we go across, that's another 32 bits. Well, let's look at a little bit of what's in the IP protocol. Most of our looking we're actually going to do in the subsequent segments. So first of all, the IP header here includes various fields which meet pretty straightforward needs. They're interesting to look at, just so you can know all the details, but I'm not really going to spend any other time than this slide to go into them in detail. They're things which it's fairly obvious that we'll need in some ways. There are length fields. There is a total length field here which tells you how long the overall datagram is, and this one, IHL, the Internet header length, tells us how long the header is, so down to here before the data starts. There's also a checksum here, just provides a little bit of way to check the reliability of the different header. There's a version number. This version number, since this is IP version 4, that should carry 4, and a 4 there really tells us that the rest of the format is what we expect for IPv4. One that might be a little interesting to you is there's a protocol field. This tells us the higher layer protocol that's inside IP, like for instance TCP, if the payload is carrying a TCP segment. If you remember way back from protocol layering, this protocol field here is the demultiplexing key, which allows us to pass the contents of the packet to the right higher layer. Okay, so there are all of the sort of the scaffolding fields, which really hold everything together. Here are some other fields, and what I'm going to do now is just give you a quick tour to mention what fields are in there. We're actually going to go through how many of these fields are used in lots of detail in the following segments. So in this segment, I'm really just going to point them out to you, and then we'll go through them later. A very important part of the Internet header are these fields, the addresses. There's a source address and a destination address. Since the network layer of the Internet uses datagrams, every packet that's a datagram needs to include a full address on it so that the routers will know where to send it. This layer of addressing is a new layer of addressing which is not the link layer addressing like an Ethernet address. It's a layer of addressing above it. This is a new network layer address. And in IPv4, 32-bit addresses are used. What we'll go through in some of the next segments are how routers forward packets based on these addresses. And then there's a bit of other information in the header. You can see here that there are several fields which are actually used to handle the relatively simple sounding problem of networks which transit packets of different sizes. So, actually Ethernet and 802.11, for instance, can carry packets of different sizes. The largest packet on 802.11 is too big to fit through an Ethernet. So IP includes machinery that uses these different fields to handle this problem, including breaking packets, large packets into multiple smaller packets, and then reassembling them on the other side. So we'll look at some of this machinery later. And there's really very little that's left in the header. There are a couple of fields here, which we'll come to eventually, a fair bit later, some number of units further on. One is a differentiated services field. This has to do with quality of service. So IP is sort of been retrofit to provide some different kinds of quality of service. And we'll talk about that near the end of the course almost. Something we'll get to sooner is there is a time to live field. This field is used in conjunction with the error reporting protocol called ICMP. It's actually used for traceroute. We looked at traceroute and that uses this field quite heavily. So in a few segments you'll learn how that works. Okay, so we've now looked at the IP header and we've heard about some of the different fields. What it's time to do in the next segments is to go into some of the functions that are behind those fields in detail.